Welcome, friends from the conference. My name is Eduardo Madrid. I am a tech lead, a camera platform at the company that makes a Snapchat, that is Snap Incorporated. And as promised, I am going to be talking to you about some general techniques that will let you not avoid leaving performance on the jump table. I will introduce myself because in these slides, there are going to be many links to material that is very useful to understand this presentation better. It is complementary material. And I had to mention these things because they are important in the way of introducing myself. I have been working at Snapchat, as I just said. I did a presentation on 2016 that is like a precursor to this one, in the sense that back in the day, I worked on how to implement protocols that generate events. This is the presentation that deals with how to consume events. There is a presentation that goes into more detail than what I can do today on several mechanisms. The slides are available. This was the Chicago C++ users group in 2017. I also presented last year at CppCon. There is a material that you might consider interesting, which is how to improve exception throwing, that I did with a coworker and friend, Suman Anumante, at London C++ earlier in the year. I used to work in financial technologies and automated trading. So that is an area that is very heavy on performance. And I got to be able to exercise many different programming techniques that have informed what I am doing today. Okay, the work that I'm telling you today about is exclusively about the performance aspect. We don't have time for anything else. You might find me on Twitter. However, I do tend to take technical disagreements to the extreme, because I really want to learn from the people that I interact with, and sometimes that creates polemics that are not very nice, but be sure that I really want just to be able to learn, and that's why I am so intense. Okay, don't leave in performance on the jump table. What is the jump table? Well, you know, what we're trying to do is to be able to specify behavior that we don't know when we're compiling the program, that at runtime, that behavior is going to be activated or not. So this has got to be a way to map the data that the application has when it is running to what is the behavior that is going to be executed. In C++, unfortunately, we cannot create a true jump table, but we have the resource of the function pointer. So the function pointer are a piece of data that we can use to refer to behaviors. That is very important when you do things like event dispatching or dynamic dispatch, which is the mechanism that activates the correct virtual overload of an interface defined with the inheritance and the keyword virtual. Okay, in the assembler, this becomes an indirect jump, and it can be an indirection, like a call a function pointer or jump into a table. So just to warm up, let us do something really easy, which is to see how it looks in the compiler explorer. What we see here, I hope that the font size is big enough. What I have here is some toy example of perhaps a game that has sprites, and there are also objects, and this will be an example of collisions. So we have an object, and the object has a field type that tells what is the type of object, and whether it's a bullet, a torpedo, a spaceship, or an asteroid. The normal technique is to use a switch on that, a bunch of cases, and the translation to assembler is, you can see here that the the execution is going to jump to a position in a table 8 times the value of this register, which is probably the representation of the sprite type. And here are the targets that correspond precisely with the functions that we're going to be calling, okay? So this is expensive because the processor, I'm not even talking about the compiler, but the microprocessor itself doesn't know where it is jumping to. It needs to have a computation to be able to determine where it's going to land. And these kind of things are expensive, so you want to minimize these kind of indirections. Well, what are the objectives for this presentation? General principles to achieve maximal performance of event dispatching and object-oriented dynamic activation. So we're going to also see how to improve over a standard function, because there are plenty of lessons that we can learn from the mistakes made in a standard function. And hopefully, if the time allows for it, how to avoid defective benchmarking. Okay. If we have a little bit more time, then perhaps I'm going to be able to share with you a few more advanced concepts that I have that I hope are going to be interesting to you. Okay. The outline is going to be very simple. We're going to be talking about event processing and runtime polymorphism. What is the relationship? How to do good event processing infrastructure to achieve better performance. And the next thing is going to be how to bind event handlers with their execution context with many different choices and the implications of following any of them. Okay. What is event processing? We need 3 components, okay? We need to specify a behavior. In C++, like I said, we cannot do the equivalent of a switch statement, but we can have something like an array of function pointers or function pointers in general. So the only option that the language allows us is using function. We need to inform the behavior of what happened, what is the event, and we represent events with call signatures. The call signature contains all of the arguments or the arguments are precisely the description of the event. And we need to be maintaining a constant execution for the event handlers. Again, this is just warm up. This is probably not necessary because I requested that the audience would have at least an intermediate level. But I think that it is a good idea for us to get in sync. So let's go over a very simple example. Let's say that we're working on a strategy on the automated trading space. It's going to be receiving market messages from the exchange through a component in software that is typically called the feed, the market data feed. And let's say, for example, that the event at hand is that there is a new order to buy Apple at $125 for a quantity of 100 shares. So that'll be the event. The trading strategy is precisely the state of the trading strategy is the context of execution. And what that strategy does when it receives these kind of messages is the behavior. Again, this is very trivial, very simple, probably not necessary. But then we also give an opportunity for the stragglers to join our room. Let us talk about a toy trading system. You can describe the quotes, the messages that are going to be coming from that market data feed using a field that is, for example, a quote type. And to not complicate things more, let's say that they are just composed of trades, the indication that a match has happened, bids, offers to buy, or asks, offers to sell. Okay, we can also define that encapsulation into a quote type. The quote type will have the typically the ID of the instrument involved in the order. The price might be represented as ticks or multiples of the minimum increment. And we use integers because we don't want to go through the performance penalty of using the floating point units. The quantity and some extra details. Okay. Let's give you just one snack of the kind of recommendations that I am going to be trying to give you. This is, again, very basic, but it happens so often that I chose to mention it. If you choose to represent a trading strategy has an object-oriented interface, I see this mistake happen very, very often, which is to get the consumers of the event consume the raw event. This is a design error. What is the design error? That rather than giving to users the raw event, you should classify to the most specific type that makes sense for your application domain. So rather than processing quotes to then have to classify them inside the user's code that does the trading system to whether it is a trade, a bid, or an ask, just deliver the actual most specific type. For example, in this case, just the trade. And in this way, you can avoid replication of effort and wasteful execution. Because in this particular example, if you deliver the most specific event type, then the classification is only done once by the programmer and once by the actual execution. Also, the idea is that you should give an opportunity for the people who can do the most aggressive optimizations to just do them. A feed programmer will be in a better position to optimize the delivery of messages than a strategy programmer. This might be subtle, and this also allows more specific subscriptions. Yeah, like, for example, there might be a trading strategy that is only interested in buying shares. Okay. There is a relationship between event processing and runtime polymorphism, understood as calling functions that have a polymorphic nature. In this particular case, we need to be able, from having an object, be able to determine what is the appropriate behavior, so how to refer to the polymorphic behavior. The message in object orientation is just a call signature, and we also need to have the object that is going to be receiving the message, right? The recipient of the message. Well, the concept of message passing in object orientation is very similar to event processing. Okay, the normal implementation of the mechanism of runtime polymorphism in C++ is using a virtual table. So when you have something like this, a very simple piece of code, let us see it in the compiler explorer. What you're going to be seeing is that first you have to resolve one indirection. You inspect what this code is receiving is a pointer. That will be the pointer to the actual object drawable, and has the first member of that object. There is going to be another pointer that is going to be the virtual table pointer. So in this particular line, what you're doing is to load the virtual table pointer, and then you compute an offset into the virtual table pointer that is going to tell you exactly what the actual function that you had to call to do the drawing in this particular example is going to be. And now that you know what is the address where you're going to, you jump there. Okay. So in object orientation, a concept that is truly important arises and is the basis of all of what I'm going to be talking to you about, which is the concept of subtyping. Okay, but I am not referring to subtyping understood as subclassing, but the concept of subtyping understood has in this very famous paper by Barbara Liskov that we now commonly refer to as the Liskov substitution principle. A subtype, so something is a subtype, so a concept is a subtype if all of the elements that belong to that concept can be substituted and the program will continue to work fine. That is the essence of the Liskov substitution principle. The good news is that the colleague Klaus Egelberger gave a fantastically good presentation about the solid principles earlier in the conference, and I wholeheartedly recommend you guys to watch it at your convenience because it's probably going to be helpful to understand the more theoretical and important basis for the important basis for the work that I am presenting to you. Okay, what we're trying to do is to improve support for subtyping relationships, especially those that are hard with classical object orientation. And a secondary objective, but the one that I have the time budget to talk today about, is to claw back on the performance penalties of supporting subtyping. I know that this sounds theoretical, but believe me, this is what we are really trying to do. And if we understand it clearly, we're going to have a better chance of succeeding at it. But let's go back to the mapping between runtime polymorphism and event processing. Well, a message through a call signature is an event. A method refers to a behavior, or it is an event handler logic. An object, it has a context of execution. An object has a state, which is the same as the event handler state. So I would posit that this is an opinion that allows me to explain things easier. I think that all of dynamic dispatch on classical object orientation are specific cases of event processing. So if we study just event processing, we are going to accomplish also studying runtime polymorphism in general. Okay. Now, the really important thing is that you want to be able to maintain for event processing the context of execution of the event handlers. You need to maintain their state. If you use classical object orientation, then you need to create those objects on the heap typically because you cannot have polymorphic local variables and or polymorphic members. What you can have are local pointers to polymorphic types or members that are pointers or references to polymorphic types. And that's a big problem because you are not directly holding a value. You are actually managing a pointer, and then you can use a unique pointer or a shared pointer or something else, but this introduces complications. Another thing is how you're going to be binding the behaviors with their context of execution or state. Well, you can use global variables, you can use any form of shared state in more general terms. And this is complicated and tricky. And we will see why this is important very soon. Okay. If the variability of the different types that are going to be polymorphic is bounded, that you know what is the complete set of types that might be participating into the runtime polymorphism, then you can use a component such as variant. Or if you don't have that luxury, then you have to use something more general, and type erasure could be a choice. And type erasure is, if you can think mentally, if you don't understand the concept yet, think about the start function. Okay, This is the last thing that I'm going to be talking about. Events infrastructure, how should it help more than the specific callback design, the design of call signatures and intricacies. Well, you should be able to factor as much as you can of out-of-user code into infrastructure code. And that's one example that we mentioned before of event classification. You also need to deal with the maintenance of the state. Something desirable would be programming interface installation and normalization, and to reduce the boilerplate. However, there is a problem. I do not have enough time to cover all of the aspects that I think are interesting. And this is something that introduces quite a lot of anxiety. So what you see in my Bitmoji graphic is the opposite of how I feel. I feel that the lack of time, rather than allowing me to chill and relax, keeps me very, very anxious. But well, I try to use this Bitmoji as inspiration to let go of the things that I want to share with you, but I don't have the opportunity to. Okay. Now, let us get into the subject matter quicker. The general case, we're going to, on a first approximation, use an object-oriented interface to model the polymorphic behaviors that we want, okay? And we know what this implies. We use inheritance. We need to never forget to make the destructors also polymorphic or virtual. But very quickly, we end up facing very hard problems to solve. Like, for example, how are you going to be doing the copying? Because now there are two different ways to do the copy. You can just copy the pointer or create a new object, cloning it, and referring to that new object when you do a copy. Equality is something hard to implement in a runtime polymorphic because the cardinality of the arguments for equality is 2, not 1. So you have to have something that is polymorphic in both sides. And then you have to maintain the value, how you're going to do it, unique pointer, shared pointer, some other mechanism. There is, I can talk for days on the problems of object-oriented interfaces. Fortunately, I have something to refer to, which is a great resource, and it only takes 25 minutes. It is this presentation, classic, many years ago, by Sean Parent, Inheritance is the Base Class of Evil. I need to recap, what are the horrors that using object-oriented interfaces have? Well, they have awful performance, and I can prove this to you because at the very end of the presentation, I'm going to show you how I can accomplish runtime polymorphism with better performance, slightly better performance, and sometimes substantially much better in others than the intrinsic mechanism in the language for runtime polymorphism. The real problem from the perspective of modeling is that the object orientation interfaces are intrusive. You can have perfectly great types that are already working and they have a very good functionality and testing, and they're just perfect. But because they don't inherit from their correct base class, you need to wrap them, and well, that introduces a big problem. Another issue is that the situation that you find yourself in is that this is take it or leave it. This is how the language itself is specified, and you cannot change any detail there. There are no choices that you can make. Like, for example, you cannot design a different virtual table in which the things are organized in a different way to accomplish your goals. I already mentioned that you cannot have polymorphic local variables. And the reason is that the compiler doesn't know what is the size of the actual implementation, and there are no ways to specify the ranges either. So that's really annoying, but that's the way it is. Okay. So the problem is that when you wrap perfectly good types into an object-oriented interface, they get polluted with referential semantics. They change the memory layout by inserting the visual table pointer, so it has a number of implications that are all very nasty. And these things lead to error-prone busy words. You already had very good types. Why do you need to wrap them? So that's very annoying. Okay, so inheritance and virtual member overrides cannot have local member variables. Allocations are super expensive. They introduce one indirection that is performance hostile. They worsen the memory locality. The data is all spread out in memory. They also become a big incentive to use share state more than otherwise. And this disables local reasoning, which is not bad, not good at all. Okay. The indirection is something that I already mentioned. One thing that people don't quite realize is this part, that the use of referential semantics forced by polymorphic interfaces may change things that were no except true, that were just going to work fine into things that now can fail because a heap allocation might be involved. Well, this difference exacerbates the performance and binary size penalties of using exceptions. There's also the possibility of an error, so the responsible programmers have more work to do. I also mentioned that the memory locality and fragmentation get worse. Also, the use of virtual overrides dumps massive amounts of things that can only be described as crap into the binary size, the object code size, that are the standard type infos from those artifacts in the middle that are not really useful. And the interfaces for runtime type information are not good at all. But you still have to pay the full price for them, which is quite annoying. Okay. Another thing is that inheritance only supports one type of subtyping relationship, which is monophyletic subtyping. This is the first time that I have done in a public forum the introduction of this jargon. Monophyletic is the only one supported, but there are also paraphyletic and polyphyletic. I will explain them at the very end of the presentation if there is the opportunity, but this is really a very important thing to bear in mind. It's just that if we want to concentrate on the performance, we had to skip a few things. I have prepared a presentation. It is called Type Erasing the Pains of Runtime Polymorphism, to really explain these things, but alas, I have not gotten accepted yet. I make some claims there that are unbelievable because that complicates things, but everything is absolutely true. So I am in the vicious cycle that I have material that I want to share that is unbelievable but true, and I need to be able to convince more people that I should give the opportunity. I should get the opportunity because then I deliver, and people get surprised, and I get more opportunities. But that is a process that takes years, apparently, and where we're doing it. But keep on the look for this name, Type Erasing the Pains of Runtime Polymorphism, because it's probably going to be my most important presentation ever. Okay, would like you to start deprogramming yourself about using inheritance for subtyping. Okay, now let us move on. There are better ways of doing this. Some needs of polymorphism. Like, for example, using the type erasure component of a standard function. There's a problem. The performance of common implementations of a standard function are very bad. And a standard function itself has gigantic design mistakes. So we're going to start talking about them. Okay, so just to introduce the problems, let us see a standard function has implemented in the standard implementation for the compiler GCC. Well, this code is very simple. Maybe I should just open it in the Compiler Explorer and talk to you about it in the Compiler Explorer. This guy, I'm going. By the way, this is just the generated code with Clang's or LLVM's standard library, and at a glance we can see that it is similar, not particularly good. So we're going to forget about this for a moment. But you have a call signature. Okay, this is the return type is void, and it has these arguments. And we defined the order consumer to be a standard function of that signature. Okay. So what is the translation when you do something like invoking that order consumer with a set of arguments? Okay. So all we're doing here is to forward the arguments that get passed in, forward these arguments to the actual target that resides inside the order consumer. Okay, well, the assembler generated is this. And I think this is absolutely not acceptable because, again, all that we're doing is to forward parameters that we already have to the target. Okay. If we try to understand a little bit of what's going on there, there is a jump on equal here. So what it is happening is that this thing is comparing some internal data member that might be a null, typically the null pointer. And if it is the null pointer, it's going to call throw function call. And if not, then the execution continues and ends up calling something at the offset of 24 bytes after the beginning of some object. And well, that's the way that presumably is going to activate the target. I know that it will, so I know that that's what happens. So the only useful work that we have is what I have highlighted in yellow, but there is a lot of garbage, dubious code in the object code, and this jump on equal and the call throwback function call that I think we can completely eliminate for the call side. So let us try to read this slide from the bottom to the top. So, so we begin, the order consumer is a sub-function, but the sub-function has two arguments. It requires a type erasure provider and a signature. The signature is the same thing that we had before. Now, what is the type erasure provider? This type erasure provider is something that I call any container on something that is a template argument called normal policy. What is a policy? Well, you use the policy builder protocol in the SUD type erasure framework. And this means an array of 2 void pointers. So I can tell you what this means is that the local buffer to hold data and the state of the target is going to be up to 2 void pointers. So we have 16 bytes of budget available to store things locally. And if those 16 bytes are not enough, then we're just going to put there the pointer to something on the heap. But hopefully we're going to be reducing drastically the amount of allocations because we are at least indicated boundaries to when are we going to have what is the bounds for the sizes of the arguments that we're going to be able to hold locally. And this also respects alignment. Okay, a policy also takes something that we call affordances, which is the set of capabilities that the any container will be able to do. And what are those capabilities in this particular example? It's going to be normally destructible, normally copyable, normally movable, normally copyable, and is also going to have the normal RTTI. So this thing with this policy very, very closely resembles the standard function. As a matter of fact, I have several code bases in different employers or past employers and my current employer that use this as a replacement, a drop-in replacement for a standard function. And I don't get reports of any kind of problems, or actually seldom reports for issues. It's mostly it's tight differences because the design is slightly different. It's better. Okay, so let me show you what happens when we use a standard function, subfunction instead of a standard function. This is all of the assembler. So let me do live the substitution so that I can drive home for you the difference. So what I am doing now is to go back to using the standard function. Oh, yes. So that is using the standard function, all the crap that we saw before. And this is the equivalent using the Subtype erasure framework. Okay, I hope that you see that the difference is quite dramatic. I'm going to return to showing you more demonstrations like I just did, but I want to make sure that I'm going to have the time to tell you very important things, and I think I'm going to be able to do it, but momentarily what I am going to do is to show you how to what happens when you jump here, okay? Because you might be thinking, well, perhaps on what we are able to see here, it is very short, but there might be a lot of inefficiencies on the other side. Well, it's not the case. So I'm going to be able to do this very easily because I am going to create a function that returns an ordered consumer. And what I'm going to do is to just take a pointer to a function that has that signature. This is not different to what you would do with the normal component of the standard function. And look what we get. In make, what we're putting at the return value is this thing. And if you see, RDI is where we're building the object. And what we're doing there is to put this symbol, function destroy. This scrolling is going to be faster. Invoke target. And what is invoke target? Well, invoke target is at the very top. And what it does is to just jump to that function pointer in particular. So what I have shown you is that I'm not cheating. The work is truly minimal, both in the part of what the compiler inserts to jump into the trampoline, and the part of from the trampoline to the target specified by the user. Okay, let me show you a benchmark in Catch 2. I'm going to show you the source code momentarily, but let us just run that guy. I'm going to make this bigger so that people can see. Actually, that's not what I meant. What I meant is a larger font. And what this thing is going to be doing is to measure the speed of execution with different levels of entropy. So what this benchmark is doing is to call alternatively in a random way, so that the branch processing units of the microprocessor cannot predict where the execution is going to be next, or not most of the time, between two targets that are going to be doing different work. And they have to execute invocations, multiple thousands of invocations to either of both targets. And these are the results that we get, okay? So in the case of Sue, actually, let's start with the plain function pointer. The plain function pointer takes about 46 microseconds to do this on the average. However, the standard library takes about 81, 82 microseconds, probably 86 microseconds. This is just repeated. And the Sue function takes, compared to the function pointer, it's some overhead of a few percentage points, but it's not so far. So this is with a maximum entropy. Like the two targets are going to be switching randomly most often. So that is the hardest for the branch predictor. So I am basically disabling the performance inefficiencies, hiding capabilities of the microprocessor. And we're seeing that Sue function is very close to using the function pointer, which, as I explained before, is the theoretical best. And using a standard function has quite a substantial penalty, about 70% or something thereabout. Now, let us skip to when the pattern of calling is far less random, like there is a random switch only once in 256 invocations. And now we see that because the things are far more predictable, the Sue function that has an inherent performance penalty of a double call, because that's inherent that you cannot do a trampoline that doesn't jump twice, doesn't have enough opportunity to hide that performance penalty, so it doesn't look as good as the function pointer, but the ways in which there are no ways to hide the inefficiencies reveal surface how truly inefficient the standard function is, which is 3 times as worse as using a plain function pointer. Okay, I think I have the link to the code. So this is publicly available. When you receive these slides, which I hope is going to be very soon, you're going to be able to look at those things on your own. And what I am doing is to call this function evaluate a number of iterations on a collection, so it's a double traversal. And here is the executable. And this executable might be either function 1 or function 2. And the way that these guys are generated is in generate functions, which uses random and a distribution that varies between 1 and 256. And it's going to insert either one depending on the distribution value, right? So all I wanted to tell you about these particular benchmarks is that the entropy is truly important. The performance looks completely different if you use something that is very easy for the branch processing to predict in the microprocessor versus something that that is not. Okay. How such a big improvement was accomplished? Okay. Well, there is the saying that there is no free lunch, right? So something weird happened here because it seems that it's just superior. Well, the thing is that there are multi-decade performance oversights that I detected and corrected. So to explain what were those performance oversights, I can just rely on the wonderful work of my colleagues at Facebook that noticed what I told them at CppCon last year, which, by the way, shows how important it is to participate in conventions. And if you see here, I am even credited with that improvement. Like they check on the history of a previous component that I have improved upon, but it continues to be usable. The same ideas were also present in any callable. And this is where they are explaining the extreme differences that, for example, in check 4, in Foley function used to be this cogen, and after they applied the technique that I showed, it is only this generated cogen. So they have put in practice some of the techniques. And what are they? Well, if you look at these, one of them is that they were putting the trampoline address as the first argument in between the user activation of the trampoline and the activation of the target by the trampoline. So rather than being it the first argument, they are now using it as the last argument. And rather than just using perfect forwarding, they are now doing something smarter, which is to use callbacks that in reality is if it is some trivial value, then use it as it is, and if not, then use a forwarding reference. Okay, I can explain that better, but and you can see that in this change set, that's why they keep repeating. And by the way, again, this is the public Facebook Foley GitHub repository, so you can verify this on your own. I'm going to explain this better, but I just wanted to mention just another thing more. The last time I checked earlier today, they still have this conditional definition, the conditional compilation proviso, which is that if they are compiling on their Microsoft MSDC, then they're going to use the old style and inefficient way of passing the arguments in the trampoline. And if not, then they feel confident about using the optimized argument passing. Well, I am proud to say that subfunction delivers all the goods in Windows, has been delivering it from the very beginning. Something that takes me a lot of time is to make sure that things work in Windows, but yeah, they do work in Windows. Okay, so what are the improvements that were incorporated in Foley? Number one, you don't check for the null pointer. You don't pay for that by making sure that you initialize something valid in the first place. That's so important. And there's repeating. Remember that Alexander Stepanov, in the seminal work that he did on elements of programming, he says very explicitly that if you default construct something that is just partially initialized, it is in a meta state, not properly initialized. That is a code smell. Okay, I've had an argument that this does tie precious branch predictor resources, so you don't see a performance penalty directly because you are not going to be calling an empty trampoline in your code. So the conditional check is always false for null, but there is a conditional check there. So the branch predictor resources that you would be able to use for something else are being used there, and that can introduce also the problem of false sharing for the branch predictor slot, etc. But this is very difficult to measure, so I haven't been able to come up with a good test to surface. But I know that it happens, and I know that it is important. I will give you a rain check on that. Okay. So another thing that you must avoid is to mess with the user types, turning them into references for no good reason, even if you want to forward them. So we refer to this as better than perfect forwarding in Sumanta Numante's a nice presentation on how to improve in section throwing early in this year, okay? So you can either go to the video link here or to the step 3. And another thing that is so obvious, do not change the application binary interface order of the parameter. So remember that if you call an instance member function that is opaque to the compiler, that this argument is going to be implicitly be put as the very beginning of the parameter list. So that makes a very big performance disadvantage. Okay. So more the design lessons here. I think the standard function is not the correct name because, you know, even myself, years ago when I was not able to implement equivalents to a standard function, I used to see a standard function as something kind of magical that somehow it itself became the target that I was giving to it. Well, nothing magical happens. My implementation, for example, uses portable C++. That's one of the reasons why it works in Windows. So what it is actually is a trampoline. It's something that you jump to the trampoline with intention of not staying on that trampoline, but to the trampoline will take you to somewhere else. Well, I call that a double call, or the trampoline compression and release phases. So if the standard function would instead be called trampoline, then it would be clear that there is a double call, and that would hopefully make the users think twice about using expensive to copy types in the call arguments. And hopefully that would prevent a mistake that developers may make, that they might privilege the case of not introducing a performance penalty when the argument is expensive to copy by using forwarding references when you shouldn't. Okay. I just touched on something that is important. Please pay attention because this is something essential. There are two different cases that function pointers refer to. One has an instance member function that has a this. So a call signature can have two ABI cases. something that is an instance member function with a this pointer, or a non-instance member function. And the difference again is that one has the this parameter at the beginning and the other doesn't. So if you mix the two, the consequence is that you're going to be shifting the whole argument list and unshifting the whole argument list in between trampoline, compression, and release. So you can prevent that problem as a user by leaving a courtesy parameter of void pointer as the first argument. So that is in case something needs that for the this pointer to be able to use it. And as an infrastructure maker, you put your trampoline at the very end of the argument list. In that case, if everything becomes a tail call, no extra work is going to be needed. Okay, I am going to stop a moment. I'm going to check the remote platform because I want to see if there are questions. Okay, what work are the strenuous operations in the standard function version doing exactly? I just went over it, thank you. How one spot that those instructions are in fact unnecessary and saw a performance hit? Okay. Yes, this is possible to incorporate into the standard library. I have not attempted to submit a proposal because the evolution of a standard function in the standard library is something that I do not quite agree with. Yes, Phil Nash, I will do my attempts to explain how to type erase the pains of runtime polymorphism at any opportunity that I have available. Thank you. Yes, I am going to be showing things that Sue can do or not later on. Yes, I have measured standard function and Sue function and many other implementations pretty extensively, and it is comprehensively superior. I just don't have the time to share more important things with you. Okay, I understand that I have probably about 10 more minutes of presentation time. So I'm going to continue until I get the plug out. We are close to the ending. As you can see, there are not many slides. Thank you for the questions. I think they were awesome. Fortunately, I was presenting and giving the answers anticipated, so we were on a parallel, synchronized state of mind with my audience, and that's amazing. Thank you very much. Okay, more things to learn. So, pointer to instance member function are static or standalone. Functions are fundamentally different. A wrapper to call an instance member function is one extra indirection, period. Different types, they work differently. Do not introduce that indirection. Then, another problem of using the instance member function pointers or instance member functions in general is that they prevent you from following the last advice of using your artifacts at the very end of the parameter list. By the way, years ago, I have been submitting variations of this presentation proposal many times. The reviewers would not believe that the performance difference would be so big. And the reviewers of my presentation proposals would think that what I say, that the order of the arguments doesn't really make a general difference. But well, that is just the way it is. So one thing that's truly important to remember is when the calling is opaque to the compiler, because you have to do the opposite when the actual call is not opaque to the compiler. Unfortunately, I don't have the time budget to, what the hell? So it's just a very tiny performance penalty. So in a previous version of a Zool function, if I call something like a type, I would have this assembler, and it is using a conditional move equal. So I am bothered because it should be just the tail call, right? As a matter of fact, in the corrected version, it should be just the tail call. Well, almost. You first need to retrieve what is the address that you're going to be jumping to, and then you jump to that address. So that's the corrected one. But it used to be like this, and wow, the difference was just what I show in this slide. No time to explain it, so I'm going to move on. Okay, type erasure affordances. Affordances are the capabilities of what a type erasure team can do, okay? The world's authorities on affordances is the person who introduced the term, Arthur O'Dwyer. He wrote a very important article, which is the space of design choices for a standard function. I have good news. Any container, either the version, any callable or subfunction or the ad hoc that I sometimes create, it has, I think, the most powerful tools for defining affordances. In particular, it allows expressing trivially all of the proposals that O'Dwyer mentions and so much more. Another thing with maximal performance, like you can see the generated assembler and you see, wow, I think that it cannot be done better. I would really, really love to talk about the part of how to define affordances in the Zool type erasure framework, but alas, again, I do not have the time. So the anxiety is extreme. But I want to show you something truly important, that I have something that I think the Zool function or the Zool type erasure framework is the only one that has this capability. Let me show you. Okay, so the only difference that we're going to have of consequence is that now order consumer is not copyable and it doesn't have RTTI. And we are going to define, look at this, and any container that is going to use as its policy a derived table policy that brings in the whole of order consumer that I had before and introduces the affordance of copyability. So, involve consumer. Oh, actually, I have to make a change here. I got the assembler that I wanted, but the slide is wrong. And this is the second time because in the trial run, I did the same mistake. Okay, this is not going to compile. And the solution is to put the guy here. All right, so what is it that I am doing here? I am using as the last argument a copyable order consumer, and that binds to invoke consumer to the position of the order consumer, which is the move only equivalent. So the Zool type erasure framework achieves compatibility at the level of references. You have the equivalent of a base class, which is under consumer, and the equivalent of a derived class, which is the copyable order consumer. But mind you, this is not a subclass. This is like a subclass of subclasses. So it is a higher order of subtyping, because order consumer is already not a particular type, but a subtype, a concept that encompasses things that can be called with this signature. And copyable ordered consumer are that set and many more things that can be used on ordered consumer. So just real quick, not this should work. So an ordered consumer is not copyable, but I can do this. And we can also, I guess, to emphasize that no R value trickery is happening there. It can give, the copyable order consumer can be copied and assigned and all those things. But again, I don't have time to go over that minutia. As usual, no performance penalty that is not inherent. And again, I think this is the only framework that has that advanced characteristic. Okay, so why is a standard function a bad design, in my opinion? And by the way, I don't need to be apologetic to Douglas McGregor and the geniuses that gave these components to us. It has happened elapsed 20 years, so we are able to do better now. Okay, the name. I have said that it's a trampoline, but the real problem is that it violates the single responsibility principle. It does type erasure, it has an affordance of callability, but because it does all of type erasure and it's not configurable because it does everything in a take it or leave it way, then if you have a lambda, for example, that has a capture that is not copyable, you cannot use a standard function with a non-copyable lambda. You cannot say, hey, I want this size for the local buffer or some other size. So real quick, size of auto size OC is size of order consumer. So that is a size of 40, and because I know how to play with this, so if I change this and I reduce from 3 void pointers to only 1, then it's going to be 32, just like I expected. So I can make it the size of a cache line, for example, 64 bytes. So you cannot even configure something as elemental as the size of the internal buffer. Again, not honoring the single responsibility principle. Okay, why is Su better? Because it has a stronger theory. I am very proud of this component. Okay, so there is a less general case, which is the bounded variability. When you know all the types, Mateusz Push is your guy. Please check on his presentations or any of the conferences of importance. But again, variant implementations do suck. And now it is not obvious performance mistakes on the part of the developers, but harder things that the compilers and the language are not able to do today. But we at Snap, we have found workarounds that are truly working, and that's a bonus that I have if I had the time to show you. But again, I'm gonna just swap to Remo because I think that I am in the margins of the time for the presentation. Chris, there is not a place to get more detailed info about this except the materials that I am linking to you with, okay? You will see a couple of important links coming up in the presentation. And why is the material not available? Well, it is a complication that I work for my employer, Snap, and probably I have my very best ideas while inside Snap, but I had to ask for authorization to make a public version of those improvements. And another thing is that if you see the evolution in time, this has changed dramatically, especially since I have had the great help of my coworkers at Snap that have been truly inspiring for me to continue working on these things. So this is changing on a fundamental level. Like what I am going to do is to introduce the concept of Gasper Ashman's CRTP sandwich to the implementation of affordance sets. And I think that's going to be a very significant improvement. So things are going to be changing. So I am actually running far ahead of a settled set of components that I can tell people use these because I'm not going to be changing them. I think that people are going to be interested in using the very best that I have, and the very best is the leading edge, and they had to talk to me personally. Sorry. Okay. Bonus section. Oh, I am so great.
We actually are out of time, unfortunately. We're going to have to cut off here and have people follow up with you after the after the talk.
Okay, that's perfectly all right. It has been a pleasure to share all these things with you guys, and I'm going to be available for social interactions during the rest of the conference today, and probably you can follow me on Twitter. Okay, I'm going to stop the recording on my side, and thank you very much for your attention.